Somewhere in the world right now, a concrete giant is being born, capable of spanning a space as wide as an entire basketball court, and all of this without a single support. How can a lightweight hollow slab withstand the weight of hundreds of tons? Why do builders say that within these slabs lies the power of steel muscles? And most importantly, what secret makes them so unique that annually in North America, over 17.5 million square meters of these structures are produced, the area of 30 pentagons? Stay until the end, and you'll discover the secret that will forever change your understanding of concrete. The Slipformer machine crawls along a 590-foot forming bed at approximately 4 feet per minute. Doesn't sound terribly fast? Now let's do the maths. That's 200 feet per hour. That's nearly the length of an Olympic swimming pool, born from concrete in less than an hour. During a single 10-hour shift, one such bed can churn out almost half a mile of perfectly formed concrete slab. Now for the main feature, the voids. These holes inside aren't simply for aesthetics. They reduce the slab's weight by nearly 50% compared to a solid slab of the same thickness. Imagine constructing an office center with a floor area of 100,000 square feet. If the floors were made from ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just removed 2,000 tons of excess weight from the building. That's the weight of roughly 500 adult elephants, which foundations and columns no longer need to support. This allows the entire building structure to be made lighter, more elegant, and most importantly, considerably cheaper. But how can such a lightweight slab be strong? The secret lies in those tension steel muscles. The concrete used in these slabs isn't what you have on your pavement. This is high-strength concrete, withstanding pressure exceeding 8,000 pounds per square inch, whilst ordinary concrete manages only 3,000 or 4,000. And the steel cables inside are tensioned with such force that they create constant compression within the slab. That's precisely why these slabs are adored for constructing car parks, supermarkets, and open-plan offices. Annually in North America, over 17.5 million square meters of hollow core floor slabs are produced. This figure simply doesn't fit in one's head. It's an area sufficient to construct 30 buildings as gigantic as the Pentagon. Every year. This isn't merely a building material, it's an entire industry built on speed, efficiency, and intelligent use of resources. Everything begins not in a concrete mixer, but on a gigantic, perfectly flat aerodrome inside the workshop. This is the forming bed. Imagine a perfectly level, polished steel runway several feet wide, but in length 400, 500, and sometimes 600 feet. Beneath this runway lie pipes through which hot water or steam circulates to keep it warm. At both ends of this runway stand massive steel anchors embedded in thick concrete foundations. Between these two anchors, high-strength steel cables or strands are tensioned. This isn't ordinary wire. It's several steel threads woven together, each capable of supporting the weight of a motor car. They're laid along the entire length of the 590-foot bed, forming the future skeleton of the slab. One end of each cable is securely fixed in the anchor. To the other end is connected a gigantic hydraulic jack, and this jack begins to pull. It tensions each of these steel cables with a force of 30 or 40,000 pounds. The steel muscles tense up, becoming as hard as the strings of a gigantic guitar and store colossal energy within themselves. This is secret number 1, pre-stressing. When the steel skeleton is tensioned, the main character enters the stage, the forming machine or slipformer. This is one of the most astonishing machines in the construction world. Imagine a strange, squat, self-propelled creature that slowly crawls along rails beside our long bed. At the top, it has a large hopper into which concrete is poured. But this isn't ordinary liquid concrete. This is so-called zero-slump concrete. It's so dry that it resembles damp earth. And so this machine begins its slow journey. Secondly, special vibrators and compactors with incredible force tamp this dry mixture, making it extraordinarily dense. And thirdly, most importantly, inside the machine are special forming tubes that, whilst vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth voids. The machine, like a gigantic concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab. Because the concrete is so dry, it instantly holds its shape and doesn't spread. This is secret number 2, voids that make the slab 50% lighter than a solid one. When the machine reaches the end of the 590-foot bed, its work is complete. But our slab is still green and weak. The time arrives for a spa treatment. Workers cover the entire length of this concrete ribbon with enormous insulating tarpaulins. Hot steam is fed beneath these tarpaulins. This creates a sauna effect that dramatically accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength. But in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened, the moment of release arrives. Workers slowly release the tension on the hydraulic jacks. Now it's not simply concrete, it's pre-stressed or compressed. This means that when a load acts upon it from above, attempting to bend it, it must first overcome this built-in compression force. This is precisely what allows it to span enormous distances without additional supports. And the final act of this performance? Cutting. Along rails beside our long concrete ribbon travels a gigantic saw. This is a monster with an enormous disc covered in industrial diamonds. With a deafening roar and fountain of sparks and water, this saw cuts the slab with incredible precision into pieces of the required length. Ready, perfectly level, lightweight, and incredibly strong slabs are lifted by gigantic cranes and loaded onto lorries. Imagine a substance that doesn't melt, leaves not a single drop of water, and simply vanishes into thin air. It can freeze anything within seconds, create thick white fog that rolls across the ground, and even stop life itself if handled carelessly. Dry ice isn't just cold, it's a controlled force of nature that humans have learned to harness. Deep beneath the hum of compressors and swirling clouds of white vapor lies a process that seems like magic, where gas transforms into solid matter at -78 degrees. But where does this gas come from on an industrial scale? And why is dry ice production considered a genuine environmental miracle? Watch until the end and you'll see how something so cold can become one of the hottest businesses in the world. Industrial dry ice is nothing other than solid carbon dioxide, which freezes at the extreme temperature of -78.5 degrees Celsius. Put simply, it's the very same carbon dioxide we exhale with every breath, which plants absorb and which gives fizz to your favorite carbonated drinks. Unlike ordinary ice, which melts into water, dry ice possesses a remarkable property: sublimation. It transitions from solid state directly to gas, bypassing the liquid phase entirely. That's why it's dry. It leaves no puddles behind, simply disappearing into invisible gas. This unique ability to cool instantly and evaporate without trace has made it indispensable across dozens of industries. In medicine, dry ice is a genuine guardian of life. It's used for transporting vaccines, donor organs, and blood, where every second's delay and every extra degree could cost a life. In cryotherapy, it's applied for targeted freezing and removal of warts. In the food industry, it's become a guarantor of freshness. Frozen products, meat, and ice cream are transported in containers filled with this cold wonder. And in the world of entertainment, dry ice is the chief instrument for creating magic. The thick, heavy fog rolling across stages at concerts and theatrical performances, or smoking cocktails in bars, all of this is the work of dry ice, which creates impressive visual effects when it contacts hot water. Dry ice production takes place at cryogenic plants. These facilities occupy enormous industrial areas, comparable to several football pitches. At the center of the site stand gigantic cryogenic tanks, steel towers up to 50 feet high, capable of holding up to 100 tons of liquid carbon dioxide. Inside the workshops, there's a constant hum, powerful compressors and hydraulic presses at work. From the giant tanks, liquefied gas flows through thick, frost-covered pipes into the very heart of production, the pressing installations. These machines are absolute monsters, capable of compressing up to 500 kilograms of dry ice in a single minute. When liquid carbon dioxide under enormous pressure bursts from the nozzle into a chamber at normal atmospheric pressure, rapid expansion occurs. This process, known as the Joule-Thomson effect, causes the gas to cool and freeze instantly, transforming into loose, snow-like dry ice. A cloud of thick white vapor rises above the pressing chambers as powerful hydraulic presses, with force measuring hundreds of tons, compress this snow into dense, heavy briquettes or fine pellets. Conveyor belts move continuously, carrying away the icy blocks. They pass through refrigerated tunnels where temperature is kept below -40 degrees. Automated machines slice large slabs into smaller pieces or transform them into pellets the size of peas. Packaging machines work at lightning speed. Precisely calculated quantities of dry ice are poured into special polystyrene thermal containers, from small 1-kilogram packets to enormous containers holding hundreds of kilograms. Automatic sealers hermetically close the packages to slow the sublimation process. In 1 hour, a single such plant can produce about 5 tons of product. Now imagine the working conditions in this frozen kingdom. In zones where presses and packaging lines operate, temperature stays below -40 degrees. Workers here resemble polar explorers. They're dressed in multi-layered thermal insulation suits, wearing special gloves on their hands, since direct contact with dry ice causes instant and extremely painful burns. On their faces are protective goggles and masks, as high concentrations of carbon dioxide in the air can cause dizziness and suffocation. Because of this, powerful ventilation systems must operate in the premises, constantly refreshing the air and maintaining safe oxygen levels. To avoid hypothermia, workers labor in short shifts, alternating work in cold zones with breaks in warm restrooms. Many processes are maximally automated to reduce human presence in extreme conditions. But even with such protection, work at these plants demands incredible endurance and the strictest adherence to safety procedures. So where do plants obtain carbon dioxide in such colossal quantities? The secret is that they don't produce it specially, they collect it. It's a byproduct of other major industrial processes. The main sources are ammonia and fertilizer plants, breweries where gas forms during fermentation, as well as petroleum refining and cement works. Rather than releasing this carbon dioxide into the atmosphere, it's captured by special installations. The gas then undergoes multi-stage purification from impurities, is dried and compressed under high pressure, transitioning to liquid state. This process is the brightest example of industrial symbiosis and circular economy, where waste from one production becomes valuable raw material for another. But for all its usefulness, dry ice is a substance requiring extreme caution. Its temperature is so low that it can cause serious burns upon contact with skin. But the main danger lies in its sublimation. Whilst evaporating, dry ice displaces oxygen from enclosed spaces. Being in an unventilated room where large quantities of dry ice are evaporating can lead to suffocation. Tragic cases are known where people suffered fatal poisoning using dry ice to create fog and enclosed swimming pools. Therefore, working with it requires strict adherence to safety rules, good ventilation, use of protective gloves and goggles. Now let's glimpse into the future, because dry ice has an incredibly exciting one ahead. Right now, scientists and engineers are developing technologies where dry ice plays a key role. For example, in fire suppression. Unlike water or foam, dry ice doesn't conduct electricity and leaves no traces, making it ideal for extinguishing fires in server rooms, museums, or power stations. Dry ice pellets are sprayed onto fire, instantly cooling it and displacing oxygen. Another direction is cryogenic cleaning or blasting. Tiny dry ice pellets are fired under high pressure at contaminated surfaces. Striking them, they instantly evaporate, and the micro-explosion caused by rapid gas expansion literally blasts off dirt, paint, or rust without damaging the surface itself. But the most fantastic prospect is terraforming planets. Scientists are seriously considering the possibility of using carbon dioxide, which in solid form covers Mars's polar caps, to create an atmosphere. By melting Martian dry ice using nuclear explosions or gigantic mirrors, one could trigger a greenhouse effect that would warm the planet and make it habitable. So this cold, smoking material that we use today for cooling drinks might one day become the key to transforming the red planet into our second home. This proves that even the most ordinary-seeming substances conceal within them boundless potential that humanity has yet to unlock.